Welcome to the boundary layer and turbulence talk. This will cover the boundary layer, vertical mixing and horizontal mixing. There are several switches in the model that relate to subgrid turbulence and mixing processes. One is the boundary layer selection, BL PBL physics. Others relate to the turbulence and diffusion, Diff-Opt and KM-Opt. So this talk will cover these options. The PBL scheme interacts directly with the surface through the surface fluxes that were provided by the land model. These fluxes have to be distributed by the PBL scheme vertically, and usually we're representing thermals in a convectively unstable boundary layer, but also dealing with stable conditions where the mixing is more local. So the boundary layer part of the physics computes the boundary layer fluxes, which is the distribution of the surface fluxes through the boundary layer, that's heat, moisture and momentum, and then also the boundary layer scheme handles vertical diffusion in the whole column all the way to the top of the model. This is a diagram of the boundary layer, the top here. So the boundary layer has several types of mixing usually. There's deep thermals that go from the surface to the top of the boundary layer, but there's also more local mixing. So some schemes explicitly include a deep component, which we would call non-local mixing, but other schemes are more local, and I'll go into those distinctions. Also, the boundary layer grows by entrainment, so the growth of the height of the boundary layer depends a lot on how much of the air is entrained from above. Above the boundary layer is a stable free atmosphere, where there's mixing is just always local with vertical diffusion. A typical diurnal cycle is illustrated here from midnight until midday and then midnight again. You can see that the mixed layer grows with time during the day and then collapses about sunset, and there's a weak residual layer above, and then a stable layer develops at night as the ground cooling reverses the surface fluxes. So the boundary layer scheme has to handle this whole diurnal cycle, so it includes the stable as well as the unstable mixed boundary layer. In the mixed boundary layer, the profiles are very well mixed in terms of theta. The winds tend to be well mixed, and the moisture as well. And so this is achieved by deep and very strong eddies that the boundary layer scheme has to simulate as a subgrid scale process. So as mentioned, the boundary layer options, their purpose is to distribute surface fluxes with boundary layer eddy fluxes and allow the PBL to grow by entrainment. So we have a couple of classes of PBL scheme in WRF. The one class is a turbulent kinetic energy prediction type scheme, listed here a few options. And some of these also include a non-local mass flux term. There's also the diagnostic non-local scheme, and YSU is a typical example of that. Above the boundary layer, all these schemes also do vertical diffusion due to turbulence. This lists our boundary layer options. There are many. The popular ones would be the YSU, the MYJ, and the MYNN2 second order. But as you can see, we have a lot of choices here. Shin Hong, number 11, is also a variant on the YSU that's designed to work at, in the gray zone down to large eddy scale. So I'll refer to some of this later as well. Non-local schemes are represented by this diagram. In any PBL scheme, we're trying to represent a vertical subgrid flux, W prime, theta prime, or phi prime as a general variable. And usually there's a local component, which is just the K diffusion type term proportional to the local vertical gradient and the K parameter. But then there's this non-local term, which is represented in various different ways in these different PBL schemes. The non-local term represents mixing or eddies that are actually not proportional to the local gradient, but more deep, for example, represented here by these larger blue arrows, which are bigger than the vertical grid scale. So a lot of schemes have to deal with these types of eddies and treat them separately from the local, more diffusion-like eddy flux. These non-local terms, as mentioned here, can either be represented as a mass flux term or a countergradient or gamma term. A large subset of our PBL schemes in WRF are what we classify as TKE schemes. They solve for turbulent kinetic energy in each column, where there's a buoyancy and shear production term, a dissipation term, and vertical mixing. In the end, they're trying to just get the value of this K parameter, but based on the turbulent kinetic energy, which is this predicted variable. So K is related to the turbulent kinetic energy, which is represented by E here, through this formula. And there's also a length scale that's required to complete the definition of K and the stability function. So different schemes have different ways of computing these length scale and stability functions, but the TKE formula has this general property of having these terms in it. The schemes differ most in how they compute these other parameter parts of the scheme. Non-local schemes include an extra component in addition to the local vertical mixing. One particular type of non-local scheme is where it specifies a K profile. And first, to do this, you have to diagnose a PBL top. And then there's a cubic function in the YSU scheme, for example. There's a cubic function which maximizes in the middle of the PBL. So this K profile is a specified profile in a diagnostic type scheme. It's not predicted by TKE, for example. It's just a function, mathematical function, with a given top based on either the stability profile or a Richardson number. Then there's this non-local term, also called a countergradient or non-gradient term gamma. So even when theta, for example, is well mixed and this term goes to 0, there's still a flux given by K gamma. And this represents, and remember K has its parabolic or cubic profile, and it distributes flux from the lower boundary layer to the upper boundary layer, even when there's a well-mixed boundary layer. So it represents a non-local part of the flux that's independent of the local theta gradient. Other types of non-local schemes have a mass flux term. Instead of gamma, you have this M term, which is like an updraft mass flux. And it transports theta or heat via terms that look like this, where M is the mass flux. Some of these schemes are also TKE schemes for the local K. So they're like a hybrid of a TKE scheme and a non-local scheme with the eddy, what we call eddy diffusivity mass flux. So the eddy diffusivity part is this, and the mass flux part is this, where the eddy diffusivity can be done by a TKE method. And these are the examples in WRF of some of these schemes, which include a few TKE options here. So a scheme's output a variable we call exchange H, which is the vertical diffusion coefficient, KV, for scalars that is also needed by WRF Chem. So WRF Chem does its vertical mixing elsewhere in another subroutine, but takes this information from the PBL scheme of its K profile. WRF can also do scalar and tracer vertical mixing using these same K coefficients. So that you can turn on scalar PBL mix or tracer PBL mix, and then the scalars and tracers will be mixed by the same K coefficients as the PBL scheme. The PBL schemes themselves only mix limited variables: momentum, heat, vapor, and some specific cloud variables, but they don't mix anything else. So especially tracers, if you're running the model with tracers, you'd need to turn on the tracer PBL mix to enable the PBL to act on those tracers. Also, another consideration with the vertical mixing in the PBL is this K coefficient is quite large, representing deep thermals. And unless this scheme is treated implicitly in the numerical sense, the vertical diffusion would be unstable with such large K coefficients and small vertical grid sizes and the longer time steps. So these schemes run an implicit method which involves solving a tridiagonal matrix given the K profile and the initial variable profile to keep this numerically stable. Some schemes include shallow convection as part of their parameterization. Most of the schemes treat boundary layer mixing as dry and don't have any consideration of latent heat release, but some options do. And these use a mass flux approach, either through the whole cloud top boundary layer, so the thermals are deep from the surface through the cloud layer, or only from cloud base, where they treat the saturated eddies at the top of the boundary layer eddies. So there's a couple of different ways of doing mass flux approaches within the WRF options. And some schemes also include the capability of top-down mixing for turbulence driven by a cloud top radiative cooling, which is a separate process from the bottom-up surface flux-driven mixing. So there's the top-down cooling-driven mixing and the bottom-up heat-driven mixing. This table summarizes some characteristics of our PBL schemes. You can see that the surface layer option has to often be coupled with the PBL option. So this limits the number of surface layer choices you have based on which PBL option you are choosing. This column shows that some of them have the TKE as a prognostic variable. In the case of MYNN, it's called QKE. It's actually twice the TKE, and it's defined in the model half levels, where TKE is normally defined on the model full levels, where W is. The other diagnostic variables are listed here. Where you see exchange H, these can be coupled with the WRF Chem, because WRF Chem needs exchange H to be able to do its own mixing consistently with the PBL scheme. And some of these schemes mix both cloud and ice, and some just mix the cloud water inside the scheme. PBL schemes can be used for most grid sizes when surface fluxes are present. So idealized cases, you may not need to run a PBL scheme if you don't have any surface fluxes, but generally in any real data case you would need a PBL scheme to be able to redistribute the surface fluxes realistically. The lowest level should be in the surface layer, which is about a tenth of the PBL height, so typically we would put our lowest level within 100 meters of the ground, more likely 50 meters from the ground or 10. This is also important for the diagnostics of the 2 meter and 10 meter quantities that come from the surface layer scheme. Some of these schemes, the lowest level should not be too thin, and those are listed here. The TKE schemes and the YSU can use thinner surface layers. They're stable and give reasonable results with thin layers and account for the layer being thin. PBL schemes assume that the PBL eddies are not resolved. This is an assumption that breaks down if your grid size becomes much less than 1 kilometer, where we have another option that we call LES, which is basically three-dimensional diffusion that I'll discuss later in the talk. And this is also coupled to the surface physics and works better when the horizontal and vertical grid sizes are comparable. So PBL schemes should be used for grid sizes of 1 kilometer or more, and can be used for grid sizes slightly less than 1 kilometer, but not towards 100 meters. Here I'll talk about some miscellaneous options. For the YSU scheme, there is a topo wind option, which can modify the surface stress for terrain effects like subgrid and resolve scale terrain. Normally the surface stress just depends on the roughness length, but the subgrid terrain may also have an impact on the low-level momentum through the stress term. So this includes an extra term to allow for the subgrid terrain. It's detailed in this paper for Topo Wind 1. YSU top-down PBL mix, I've mentioned, is an option and is becoming the default in the newer versions of WRF, where it's cloud trop cooling-driven mixing, adding a term which enhances the mixing in the upper boundary layer based on whether there is clouds with radiative cooling above the boundary layer. For MYNM, we also have a wind farm option. Wind farms add an extra stress term, like obstacles, at the ground, and also add turbulence downstream, which goes into the turbulent kinetic energy of the PBL scheme. So these impacts are parameterized in the wind farm model that's coupled to the MYNN PBL scheme. Gravity wave drag is another process that can be added in the model. It's typically used in global models which have low resolution, greater than 5 kilometers, for example, grid size, because there's gravity waves generated by topography that do important momentum transport but are not resolved at those kind of grid sizes. And these gravity waves also break in the upper troposphere where they deposit drag, and so that can modify the speed of the jet stream, for example. When you're doing long simulations or global simulations with mountains, you often need this kind of term. When your grid size is fine enough, like less than 5 kilometers, you're resolving the mountain waves that do this momentum transport from the surface to the upper troposphere. So you don't need these terms. So the switch gravity wave drag option equals 1, which includes this effect. Another effect you can turn on is the gravitational settling of fog, which is this switch here. There is an option to run the PBL on land surface with a longer time step called bldt in minutes. Typical value is 0, so you run them every time step, but there are cases, like with the CLM land model, which is quite expensive, where you may want to consider increasing bldt to something like 5 minutes to save computational cost. The boundary layer contains a range of scales, and this impacts how you represent the eddies in the model. Typically, boundary layer eddies have scales in the range of hundreds of meters up to a kilometer, and most of the energy is in these scales. So the model resolution either resolves those scales or doesn't. For typical grid sizes in the mesoscale, you have the grid size is much larger than the main eddy containing scales. And so you can use a PBL scheme, and all the eddies are considered to be subgrid, and basically these are 1D column schemes that handle as a subgrid vertical fluxes. When you get to very fine scales, you can use LES schemes which are resolving these eddies, because now at grid sizes of about 100 meters, you can resolve eddies of a few hundred meters. So then you're getting into the LES regime, where all the eddies are resolved, and now the turbulence is three-dimensional because you're dealing with horizontal and vertical flows inside these eddies that are much larger than your grid size. Between the PBL and LES scales, there is a gray zone, which is sub-kilometer grid sizes of a few hundred meters to a kilometer, where neither the PBL or LES assumptions are perfect. There are some schemes that are now available to try and handle this regime. Xinhong PBL is based on the YSU scheme. It's still a one-dimensional scheme, but it transitions between 200 meters and 1 kilometer, where that non-local term that the YSU scheme has becomes less active as you get to higher resolution, with the assumption that the eddies are now doing all the fluxes and you do not need a non-local component because it's resolved. So this scheme transitions from a non-local scheme to a purely vertical eddy scheme. Another option we have now is the 3D TKE option, which is KM_opt equals 5. It's a three-dimensional scheme that can also be used at low resolution, where it adds this non-local term, similar to the one in Shin Hong, to allow non-local vertical transports and implicit vertical diffusion at coarse grid sizes. So it's scaling between a LES type application at high resolution, where the mixing is fully three-dimensional, to a PBL type mixing with a non-local term at low resolution and implicit vertical diffusion. Other schemes may also work in the gray zone, but they will not have the correctly partitioned subgrid and resolved energy fractions. So it doesn't do harm to your profiles to run a PBL scheme at 500 meters, for example. It's just that the scheme will either suppress the eddies or leave the eddies too strong, depending which scheme you are running. So now we come to the turbulence and diffusion part of the talk. This is where the physics overlaps a bit with the dynamics. Basically, in turbulence and diffusion, we're dealing with subgrid eddy mixing effects on all fields. The typical way it's represented is this equation here with second derivatives in the horizontal and vertical directions and k coefficients both in the horizontal and vertical directions. So one of your choices when you're doing diffusion in the model is Diffopt. Diffopt selects the numerical method, especially for horizontal diffusion, which I'll show soon. When diffusion is used with the PBL scheme, the vertical diffusion is deactivated, so Diffopt only would impact your horizontal diffusion choice. Diffopt equals 1 is limited to constant vertical diffusion, which is you can specify a coefficient with kvdiff. So it should not be used when you have a calculated diffusion coefficient, such as KM_opt equals 2 and 3, that I'll come to later. It can be used with a PBL scheme because that includes its own vertical diffusion internally. And Diffopt equals 2 is strictly horizontal for better complex terrain, as I'll show soon, and avoids diffusion up and down slopes. It also can be used with variable vertical diffusion coefficients. So Diffopt equals 1, as I mentioned, is a simpler option. It just diffuses along model levels, which can be sloped. So it only uses the point on either side to do a horizontal diffusion in the model coordinate. Diffopt equals 2 is trying to make horizontal diffusion purely horizontal. It takes the horizontal gradient, which when you have slope coordinates requires a vertical adjustment to do an interpolation to the same level. So it includes some extra terms, but it's more accurate as a horizontal diffusion choice. For stability, the diffusion strength of this option is reduced when you have steep coordinates. So it makes it more stable by reducing the strength in steep conditions. Large-Eddy Simulation is what I'll spend some time on here. For grid sizes up to 100 meters, Large-Eddy Simulation is preferable as opposed to using a PBL scheme. LES treats turbulence three-dimensionally instead of separate vertical and horizontal diffusion schemes. Explicit vertical diffusion in Diffopt equals 2 replaces the PBL scheme and can accept surface fluxes from the surface physics as input. So you can run a LES option with the full physics, including a land model. We have two choices for the K coefficient in LES. One is a TKE option with a prognostic TKE equation, and the other is the 3D Smagorinsky option, which is a diagnostic way of computing the mixing coefficient. TKE is an advected variable with the LES option, so it's a prognostic variable that moves with the wind. Of the PBL schemes, only MYNN has a TKE advection option. So normally with the PBL schemes you have TKE, but it doesn't get advected. But when you're running LES, the TKE does move with the wind as it has its sources and sinks and also advection. So to run LES mode in the model, you have to turn off your PBL scheme, PBL physics option equals 0, and use diffopt equals 2 to allow the vertical diffusion coefficient to be variable, and then KMopt equals 2 or 3, which are these more sophisticated ways of computing the K coefficients. This scheme can also be used for real surface fluxes, as I mentioned. It's best when you're using this type of option, it's best to try and match your horizontal and vertical grid sizes to get isotropic diffusion. You can treat the physics more uniformly in both the horizontal and vertical direction. And the assumptions in these schemes are better when you have more uniform vertical versus horizontal grid sizes. If you do have to have strong ratios of dz to dx, for example, when you have a high model top, dz may stretch and become much larger than dx. This can work as long as you do continuous stretching up to the top. It seems to have issues when you try to have dz greater than dx and fixed values of dz near the model top. So if you do need to have stretching, I'd recommend continuous stretching to the model top. There are several ways of running the LES scheme in WRF. Notice there's one option here called mix isotropic, which forces the horizontal and vertical length scales in the subgrid turbulence to be the same. If you don't do that, they'll depend on the respective grid sizes. The first choice you have with LES is whether to use a TKE or 3D Smagorinsky option. So for that, the difference is KMopt. You would use diffopt equals 2 and KMopt equals 2 or 3, 2 for the TKE and 3 for the Smagorinsky. When you turn on the TKE option, you have the extra prognostic variable, which is TKE. Another choice you have is related to the surface fluxes and how you're going to deal with those. This is usually related to whether you're doing an idealized or real case. For a purely idealized case, I surface flux equals 0. You don't even need a surface layer scheme because you're not running a land model, for example. So the heat flux can come from your name list. You just specify a constant heat flux. The drag is also from the name list. You specify the drag coefficient, and that gives you a basic LES in idealized conditions where you have control of the heat flux and drag coefficient from the name list. Option 1 is the more normal situation for real data cases. So iSurface Fluxes 1 is typically on for all your real data name lists. And when you do that, the heat flux is coming from the land surface model, and also the surface layer physics has to be activated to provide the land model with exchange coefficients. And then the drag is coming also from the surface layer physics via U star. So this is how the surface layer normally provides information to the rest of the physics. It also provides it to the LES scheme. Another option is 2, less used. That's where you have control of your heat flux from your name list, where you still run the surface layer physics to compute the drag coefficient. This gives more detail on KMopt equals 2, which is the TKE option for running the LES. So in this we get a prognostic TKE equation with advection diffusion, not shown, and sources and sinks. K, as I mentioned before, is computed from the square root of the TKE and a length scale and a constant coefficient. So the TKE equation generally looks like this. There's a tendency of TKE with its advection and diffusion. And then you have shear production, buoyancy, and dissipation terms. And those are listed below here. Shear production is a function of these deformation terms. These are just purely functions of the wind gradients in different directions. So the shear production is a product of the K coefficients and these deformation terms. The buoyancy production depends on the K coefficient and the stability parameter, n squared. And then there's a dissipation term which is proportional to e to the 3 halves. So this is your TKE equation and the terms in it. The ARW Tech Note will have more details on how this is done. 3D Smagorinsky option is the diagnostic form that doesn't need TKE. So the K coefficient here again is a constant and a length scale. And then it's a function of the deformation, which is this tensor of all the velocity gradients in different directions, and basically a measure of the shear. And then there's a measure of the stability, which is the inverse Prandtl number times n squared. So the stability reduces the K coefficient, and the shear increases the K coefficient. And this outlines again what that D parameter looks like when it's computed from the individual components in the tensor. Again, the ARW Tech Note for details. So I mentioned KM-opt already, but there are a few other options here. For idealized cases, you can use KM-opt equals 1, where you have complete control over the horizontal and vertical coefficients. Those will be just constants. KM-opt 2, as I mentioned, is the TKE prediction option. KM-opt 3 is the Smagorinsky option. KM-opt 4 is the one you would use for real data cases where diffusion is only used in the horizontal direction. So for that we have a special two-dimensional Smagorinsky K calculation called 2D Smagorinsky. And this will be the default in your real data cases where you're running a PBL scheme and then only using the horizontal diffusion from the model's diffusion schemes. Another variant on our subgrid turbulence parameterization is called this subfilter stress scale model by Kosovic and Maroka. This has a couple of options. One is option 1, which is an NBA, nonlinear backscatter and anisotropy option. Using diagnostic stress terms, works with KM-opt equals 2 or 3. Or there's another option that uses a TKE-based stress term. So these modify how the momentum mixing is done in the subgrid scale. There's also another switch called M-opt equals 1, which adds outputs for the subgrid stresses, in case you're interested in looking at them. So this summarizes your choices when you're using diffusion in the model. In real data cases with the PBL physics turned on, the best option is diff-opt equals 2 and KM-opt equals 4. Diff-opt equals 2 is less diffusive in complex terrain, as I mentioned, than diff-opt equals 1, which diffuses along slopes. So this is especially good for complex terrain. If it's reasonably flat, it doesn't make a lot of difference whether you use diff-opt equals 1 or 2. So using KM-opt equals 4 complements the vertical diffusion done by the PBL scheme as well. In high-resolution real data cases of the order 100-meter grid, you turn off your PBL scheme and you use diff-opt equals 2 with KM-opt equals 2 or 3. This is what we call the LES option. For idealized cloud resolving cases of 1 to 3 kilometer grid sizes, we recommend also diff-opt equals 2, KM-opt equals 2 or 3, which is the more sophisticated subgrid turbulence schemes. They work for these grid sizes as well, not just LES. With complex topography, diff-opt equals 2, as I mentioned, is more accurate for slope coordinate surfaces and prevents diffusion up and down valley sides. It still can get unstable with complex terrain. We recommend not having your slopes in the model greater than 45 degrees. As you get towards 45 degrees, you can see some instability issues sometimes. One trick you can use is EPSSM, which is a sound wave damping filter. And basically, increasing the value of that from its default value of 0.1 can stabilize the model for steep conditions and is worth trying. Valid values go up to 1. You can try high values to stabilize the model when your slopes are steep. Note that WRF can also be run with no diffusion. We don't recommend that because diffusion does represent a physical subgrid mixing that should be occurring. We do have a filter option which is normally turned off called diff 6th opt. It's a 6th order diffusive type term, del to the sixth. It's an effective way of removing 2 delta x noise. It's suitable for idealizing real data cases and affects all infected variables, including scalars. There are 3 ways of running this. Turn it off. One is the simplest way of applying this, but can produce negative water, so we don't recommend that. 2 is one that prohibits upgradient diffusion and does allow positive definiteness of water, so it keeps the water positive. There's a factor as well, diff6 factor, which controls the strength of this term. Typical value is 0.12, which is quite a strong diffusive term for this 2 delta x noise. Value of 1 would correspond to a complete removal of a 2 delta x wave in 1 time step. We only recommend using this when you see significant amounts of noise. That can happen if you're using, for example, an even order advection scheme, which doesn't have its internal damping, or if you have fairly light winds and a lot of PBL noise, and you prefer not to see that, you can actually use this filter to alleviate that noise level. Upper damping can be controlled with an option we have called damp opt. The purpose is to prevent unrealistic reflections of waves from the model top, which can be important when you have high topography. We have 3 options here. One is the upper diffusive layer. Number 2 is a Rayleigh damping, which is for idealized runs only because it damps towards your input sounding. And number 3 is the W Rayleigh damping option, which only damps W but is suitable for real data cases, and we recommend option 3 for real data cases. They're all very effective in removing this reflection from the model top. Some figures on the right show examples of its use. The top diagrams are turning it on with a 50 millibar top, just 2 different times in the simulation, 12 and 30 hours. Shows what it should look like, no reflection. When you lower the top to 100 millibars, it also looks reasonably good with the damping on. And the bottom one is where you turn that damping off and you see the problems develop over time. In 12 hours you don't see too much, but it's certainly later you see this standing wave downstream of the mountains, which is basically reflection of energy from the top, which is seen as waves downstream of the mountain that are unrealistic. It should look more like the diagram above. So when you have these kind of reflections from the top, that would harm your simulation. They're slowly developing, but generally not good to have. So what you would like to do is turn on your upper damping, in general anyway. It's not an expensive thing to run. We have some controls for this parameter. One is the depth of the damping layer. Typically we would use 5 kilometers to absorb the waves that you want to damp. And then also the coefficient, which is the strength of that damping. There's somewhat advice on the size of these coefficients in the README namelist file. But for W Rayleigh damping, the typical value would be 0.2. This concludes the PBL and turbulence talk, which covers this part of the diagram. The PBL, as I mentioned, can be represented either resolved or unresolved. When it's resolved, you're running it in LES mode, but it can still interact with the surface fluxes directly into the LES eddies, or you're running it as a one-dimensional PBL scheme where the eddies are subgrid scale and the fluxes are redistributed vertically within the subgrid parameterization scheme that does the vertical mixing in various different ways, including local and non-local.